you all for joining this talk. I'm Michael Kruse, working at Argonne National Laboratory on the exascale computing project. Loop optimizations are not only important for the next generation of supercomputers, but also for domains such as machine learning, signal processing, multimedia, and basically any program that contains for loops. I think the current loop optimizations LLVM can be improved with a fresh approach on how to represent loops. Let's start with why I'm making this proposal. At the beginning of this year, I sent an RFC to the LLVM developers mailing list. One of the responses was referencing this XKCD. I don't think it applies directly, since I'm not proposing an universal intermediate representation that rules them all, but for just a specific category of optimizations, namely optimizations of loops. Still, there's a point to it. One does not simply add yet another intermediate representation just for fun. In this case, I think my proposal adds value over the representations such as vPlane and MLIR. I already gave a talk about the shortcomings of LLVM's current loop optimizations, but because it is important, I'm going to repeat the main arguments here as well. The first problem is that writing a loop path is complicated. Currently, loop paths have relatively many lines of code compared to what they implement. Every path basically has to re-implement a profitability cost model and customize also dependency analysis. Because of all the details to consider, it is also hard to ensure no miscompilation. In addition to that, loop paths have to handle a couple of low-level issues like preserving analysis and normal forms. For loop paths, some of them are mandatory, required by the loop path manager. The next issue is code versioning. Code versioning in LLVM is used to check at runtime whether the requirements for an optimization to be valid is met. If it is not, then a copy of the unoptimized loop is executed. In this example, creating another version of the outer loop separated by a runtime condition which decides which version to execute looks like this. This effectively doubles the code size. The issue here is that paths do not know about previous versionings, meaning the amount of code is doubled every time. Here it is after 2 transformation passes, and here after 3. Without versioning, optimizations could not be applied at all because of corner cases that one would normally assume to never happen. But since it is not undefined behavior, its semantics must be preserved. What we really want is a single unoptimized fallback version. The idea is that well-written code never needs it. Another problem is that the path pipeline is static and therefore transformations can only be applied in a specific order. Depending on how the source code was written, optimizing computation kernels may require different transformation orders or the same transformation multiple times. A user may also wish to directly apply a sequence of loop transformations in a different order. Currently, things get complicated when trying to apply multiple optimization hints to the same loop. The next problem is that of conflicting instruction-oriented optimizations and loop-oriented optimizations. In the upper corner snippets, a loop interchange path can freely transform between the 2 possible loop orderings. But once a scalar optimization is applied, either register promotion on the left or partial redundancy elimination on the right, it becomes much more difficult to interchange the loops. The SSA form has baked in the loop order. If not enabling a loop optimization, a loop normal form has the potential to make the code slower or larger than necessary. For instance, loop rotation is disabled when optimizing for size, so loop paths cannot assume this normal form. This would usually be the point of a canonical form. Also, some loop normal forms contradict non-loop canonical forms, such as simplify CFG removing preheaders added by loop simplify. Instead, there is a single loop simplify CFG path that is meant to preserve the loop normal form between loop passes. Let's come to the proposal itself. Imagine for a moment that making a copy of the entire IR was cheap. What we then could do is to apply a transformation first and then analyze it afterwards, even after applying more than one transformation. Let's say we applied vectorization to a loop whenever the loop structure allows us to, without any regard to whether it is correct. Once we have the vectorized IR, we can compare to the original IR to see whether it has the same semantics. For the sake of this example, assume that it does not. Instead, let's try loop distribution. This time assume that the legality check determines it keeps the same semantics. However, loop distribution by itself might only introduce overhead in form of an additional loop, so the check determining whether it is profitable fails. But one of the loops that come out of the loop distribution might be eligible for vectorization. In this example, the loop satisfies the legality and profitability constraints and can be used to replace the original code. These checks can, in principle, be applied after any sequence of transformations, also making implementing new paths easy because they do not have to implement all these checks themselves. We can also emit multiple versions of the same code and select a version at one time. For instance, the profitability check might predict that with a large loop trip count, it will run faster when offloading to a GPU. Moreover, the runtime selector can collect the assumptions made during the analysis and code optimization, and when they do not apply, just execute the original code. Note that the fallback code skips the loop normalization. If no profitable loop optimization is found, the copies are just thrown away. This means that loop normalization only takes effect when applying an optimization. The legality checker's job is to compare the original code with the transformed code. The general problem is undecidable, but if we only move statements around, a sufficient condition is to check whether all dependencies between them are satisfied. These include flow dependencies, control dependencies, loop carry dependencies, and so on. If I could, I would also tell you how to determine the fastest code. Unfortunately, I don't know how to optimize every application for every platform that is out there. It also depends on dynamic properties that are just unavailable at compile time. The goal is merely to create an infrastructure that chooses the optimizations to apply, with very different approaches for different needs. By default, the compiler may just apply a set of hand-selected best practice heuristics that are unlikely to cause any slowdowns. More aggressive optimizations can be enabled, such as the compiler estimating the execution time of loop nests. This works differently for cyclic and non-cyclic code. For straight-line code, we already have a model in form of the machine code analyzer. For loops, we could start with an assumed average loop trip count. For instance, IBM's XL compiler uses the magic number 100 by default. Other sources for this information are execution profiles or pragmas directly telling the compiler how many iterations to expect, like the Intel compiler allows. There are other possibilities as well, such as pragmas directly telling the compiler which optimizations to apply, or maybe even a plugin that comes with the application that knows how to optimize itself. A third possibility is auto-tuning, run many different optimizations to converge to an optimum. In a JIT environment, there's an interesting decision to make, whether to continue exploiting the fastest version yet found or looking for more, maybe even faster optimizations. We can also throw machine learning at the problem. Using auto-tuning, it can autonomously learn the rules that make programs fast. One of the rules is for the mapping of the loop to the compute hierarchy. By default, we assume that a loop is sequential and execute at the very bottom of the hierarchy. But once determined that there is parallelism in the loop, there are many possibilities. For example, the loop vectorizer maps to the SIMD level, but I would argue that a good optimizer should consider the entire loop nest and all visible parallelism at the same time. This diagram shows a CPU-based hierarchy, but we can also consider a GPU-based one. For instance, a profitability heuristic might choose to map a loop to CUDA multiprocessors, but this would leave all the other levels unused. Mapping to a CUDA core on the other side would just use a single multiprocessor. Or mapping to the warp level would just use its 32 threads. A tiling transformation allows using multiple levels with just a single input loop. The CUDA programming model tries to hide the difference between warps of different CUDA cores, but effectively it is also a tiling by 32. The cheap copy is just one ingredient. Another is moving from an instruction-centric representation to a loop-centric one. This makes changing loops easier, only manifesting in the instruction-centric IR at the end of the code generation phase. Instead of changing all the instructions that make up the loop, change the object that represents the loop. Changing instructions themselves is less important in this phase. This is not a new idea. Other compilers such as Open64 and IBM's Fortran compiler already have done so decades ago. Let's take an example. First, we have a root node that represents the function. The green nodes represent statements that have side effects, such as writing to memory. Each is instantiated a number of times, as defined by the loop nodes. A loop generally only means execute something a number of times, but not necessarily in which order. For instance, a concurrent loop would have undefined order. A vectorized loop would represent vector unit lanes. Expression nodes at the bottom have no side effect and can be evaluated whenever the input values are available. They also can be executed multiple times or not at all. This flexibility allows us to ignore expressions when computing dependencies. There is no loop hoisting or syncing required. The possibility to reuse nodes means that this is not really a tree, but a directed acyclic graph. Subtrees can be reused when creating new versions. Both is possible because nodes have no references to their parents. In this illustration, the K-loop is reversed. This is only valid if S is not the minimum value. Otherwise, the loop condition is a tautology and the loop is infinite. This condition is added as an annotation to the node and will be converted into a runtime condition if this transformation turns out to be used in the final result. We have seen that nodes do not have links to their parents, but sometimes this information is required, like for dependency analysis. Think of a statement that depends on the execution of the same statement inserted somewhere else in the tree. We are using a separate tree for that. Let the green tree be the source of truth and have only references to children. A separate red tree has nodes with references to the corresponding green node and also has a link to the parent node. The same node can be reached by multiple paths, even from the same root, which means there can be multiple red nodes per green node. It also means that the red tree is indeed a tree. The red-green tree naming is a term I stole from the Roslyn C# compiler that uses this structure to represent editable syntax trees. Dependencies can then be represented as relations between red nodes. The yellow expression nodes are not used for dependency analysis and therefore usually do not need to be part of the red tree. Transformations like unrolling never invalidate dependencies and therefore should not need an expanded red tree to validate their correctness. There's another kind of tree for which recursively visiting There is another kind of tree for when recursively visiting the red tree. In this case, the path to the root can be stored on the caller stack frames. I call this a red ref and use the color blue. Maybe I should call it the blue tree? Sibling nodes get out of scope when visiting the next one and cannot be used for dependencies. And there's only exactly one path available at a time. But this exactly matches the use case of the recursive visitor pattern that I often use to traverse the tree. Different node kinds have different properties. I already mentioned the assumptions that can be attached to signal that a node is only a valid replacement of its predecessor under some conditions. Statement nodes also contain summary information like what side effects they have, values they use, and array regions they may access. This saves us from having to visit the entire subtree again if we want to transform a subtree as a whole. It requires that all side effects can be captured this way. That's what we want anyway. We don't want to hard code an exhaustive list of all instructions from the base IR. MLIR already has a side effect interfaces for such uses. Any IR instruction can be wrapped into a statement or expression node, but to do some analysis other than the side effects, some have to be interpreted. Arithmetic operations are lifted to infinite precision arithmetic to avoid that parsers have to do with signed, unsigned representation or integer wrapping. It also adds the corresponding assumption. Since we do not enforce SSA, there is no difference between a select instruction and a find node. Both are handled by their predicated in execution of statements. Accesses are converted to array accesses. Accesses are separated by memory regions that are guaranteed to never influence each other. It also might try to infer array indices, including multi-dimensional ones, if not already known from the base IR. Reductions also get their own representation because explicit reductions have looser dependencies than the equivalent loop-carried dependency chains. We have some components that might get different implementations depending on how thorough we want our analysis to be. The first component is the expression evaluator. Its job is to simplify expressions and determine whether an expression is true or false. More sophisticated algorithms would answer "don't know" less often. A simple implementation would be to normalize expressions and finding patterns. A more sophisticated implementation would use mathematical solver algorithms. General expressions can be used for closed-form expressions. These are expressions that only depend on loop counters and invariants, in other words, without data dependencies. Closed-form expressions have to be derived using the red tree. In the green tree, we do not know whether a symbol refers to a loop counter or something else. Variables can also be invariant in only a subtree. Closed-form expressions are used, for instance, to describe loop trip counts. Another use of closed-form expressions is to describe array subscripts by the array detection. Whether two array regions overlap in memory depends on the range of their subscripts. Subscripts are also used to identify which statements might access the same memory. Dependencies that can be proven to never access the same memory can be removed. This way, multiple dependence analysis can be combined to remove as many dependencies as possible. Let's now go through a more concrete example of applying an unroll and jam transformation. This example code here computes the same sum of array elements a number of times. It's just an example. The expected code after unrolling and jamming is on the right. When converted to a loop hierarchy, it resembles this structure. These are the scalar dependencies. In a single static assignment form, these would be the def-used chains. We can augment the dependencies to which statement instances they apply to. This allows us to handle them the same way as dependencies over arrays. For those dependencies induced by array accesses, we have those potential dependencies. But let's assume that the two arrays do not alias, so only this self-dependency on the store instruction remains. But since the subscript is different for each instance, no dependency is left. To apply unroll and jam, we change the step size of the outer loop to 2 and duplicate the references to each statement. To make each reference do different things, we assign different values to I before the original statement. Keep in mind that this is not a single static assignment form. From the outside, the sequences become statements with different effects, but the connection to their original statement is still available to compare to look for dependency violations. Turns out that our scalar dependencies remain in forward direction, and because there are no array-induced dependencies that we could violate, this transformation is semantics preserving. One of the benefits I pointed out before is the reuse of green nodes. They are fewer because a loop node represents multiple instructions that make up the original loop, but these nodes are also larger. To show the difference, let's first change the number of instructions in the innermost loop body from 8 to 1000. When unrolling by a factor of 16, reusing the 1000 instruction nodes 15 times instead of making entire copies saves us quite some objects. But if the profitability heuristic chooses this version, the result is the same number of instructions. A speculative copy itself only costs us the green nodes on the path to the root. Even the number of red tree nodes stays reasonable. With the summary information in statement nodes, we do not need to reanalyze statement subtrees. The real difference comes when using loop versioning. With LLVM's current approach, in worst case, the code grows exponentially in the number of passes that do versioning. Using this proposal, we only have a single fallback version per loop nest, no matter how many transformations are applied. Coming to this talk. Here I summarized what I think are the most important ideas. I do not think there can be a good implementation using vPlans or MLIR's object model. Both are based on def-used chains, which are in conflict of green nodes not referencing sibling or ancestor nodes. MLIR has the isolated from above property, forbidding accesses to shared data structures for parallelization. But in our case, we actually want to reuse shared subtrees. MLIR is also currently focused on lowering from higher level representations. This might change if Clang is retargeted to emit MLIR. The current implementation is still at an experimental state, but if you are interested in advancing this approach, please contact me. A big thank you to everyone for being here. I would also like to thank the entire community for making LLVM possible. See you at the Q&A.
Thanks, Michael, for the very interesting presentation. And here we are at the Q&A section. First question. There are multiple points of invocation of loop passes in the current pass pipeline. Does the proposed steps get run for each point? For example, the generation of tree from LLVM IR.
Thank you, Whitney, for presenting the Q&A. The first question, so my idea is that to have the loop optimizations run just once in the entire pipeline, and after that to be done with it. So no further loop optimization before or after, just a single loop transformation pass. So not to have to reanalyze the same code again. Also not to make it necessary to process the loop transformations on output. It's preferable more at the beginning of the current mid-end optimization pipeline because we may want to process the loop transformation pragmas. For instance, if a user says pragma Clang loop distribute, so that we can directly apply it without any loop passes getting in the way of applying a wish expressed by the user.
Thank you. Second question. Do you have any measurement on the compile time impact?
Unfortunately, I do not. I'm relatively early in the stage of making it work. I don't have working dependency analysis so far, which I would expect to take the most of the time there. And since I don't have that, I didn't feel make any sense to measure actually compile time. But I would more expect to go up, since it's an additional pass, and additional passes in the pass pipeline, you do not decrease the compile time, except if we would think of replacing other passes in the pipeline. But it's also one of the strengths, I think. You can make it optional. You can only enable at high optimization levels if you're interested in compile time, or maybe not have it switched on at all if compile time is more important for you.
How much effort you estimate it will take to move all existing loop passes to the proposed framework?
The biggest effort there is making the framework including the profitability and dependency analysis, because they have to be written in a very generic way. But once we have that, I think it's really easy to implement it. Each of the passes, like unrolling loop fusion, it's just reconnecting some nodes around and then pass it back to the framework to analyze, is it semantically valid? Are the dependency preserved? And is it profitable to do? So I think that can be done really quickly once the framework is available.
When do you think the framework will be available?
That's something I do not know. I hope actually to get it somewhat in a workable state at the time of this conference. Unfortunately, I did not. I toyed around quite a lot with different patterns of how to iterate over a tree and do transformations, which took some time. It's also have other things to work, and up to now it's still a one-person project. So depends on whether folks are going to help me on it.
Yes. From your experience from porting the loop unroll and jam pass, how much of the existing pass can be reused?
Honestly, not very much. So the majority of the loop unroll and jam pass is basically the boilerplate that I want to replace. So dependency analysis, the non-existent profitability analysis, and the fixing the instruction connections, the use def change, so on. All those things should be done by the framework or not by the loop unroll jam pass itself. That said, there's still some heuristics that we may want to implement directly in the unroll and jam pass, like pre-check whether the unroll and jam may violate some dependencies before applying it, just because it can be done quickly as a loop unroll and jam pass does code. So we could reuse reasonably that part of the pass, I think.
Thanks. With this framework, would there be a particular pipeline or loop passes are run in all possible order and multiple times? Isn't there an infinite numbers of possible order?
As I said, this is related to a previous question. My idea is to have the framework just run once in the pipeline, not multiple times. So there is not an infinite number. There is just run it once, but there is the relation to the loop passes, the transformations inside the framework as well. So in which order do we try to apply transformations? There is the naive approach would be like brute force, try everything transformation, but this does not scale. And I think as a default strategy in a compiler, just have to have a set of base transformations that can be typically applied with some detection of how the IR look like. For instance, if something looks like a stencil code with accessing just neighbors of the current iteration point, then we know, okay, a stencil, we know how to optimize stencils, and then we can just apply the transformations that we know are good for stencils. Or if you do not detect a code, it would just be the usual candidates of, okay, try unrolling, try loop distribution before vectorization, something that's known to be good for general loops. Other strategy could involve some, if you detect pointer chasing code, like do some prefetching and so on. So there are lots of possibilities, but the point of the talk is also not to present a definitely approach on what's the best optimization is, but enable possibilities to try out different approaches, since different use cases need different approaches there.
Right. By removing some fundamental assumption, for example, SSA, do you expect the complexity of analysis and transformations become higher?
It's by design, it is higher. So SSA gives you a really fast possibility to get to the definition of a value. And if you don't have SSA, you need a dependence analysis, which is by construction more expensive. But I think this is the point. So you have transformation optimizations which make use of SSA, but for those especially higher order transformations on loops, those need to do a dependency analysis anyway. So SSA is not really useful in that regard, but since we as I said, we need to do a dependency analysis anyway, I don't expect additional cost for not having SSA. On the opposite, even because if with SSA and dependency analysis we have two different kinds of how to handle data flow, and if we just handle it the dependency way, there is less work to do in handling just one way of representing data flow.
That's true. And if we want to run some function passes in between the loop passes, do we need to first generate the LLVM IR, run the function passes, and change it back to the tree representation?
Yes, we would, but as I said before, the goal is to have it just once in the presentation, in the pipeline. So I don't see a reason why I wouldn't want to do that.
Okay. Can any loop be lived into the new transformation, or there are some limitations?
So the representation tries to simplify what the representation of a loop is. So we do not, such that passes do not have to care about multiple loop exits or irregular control flow and so on. So there's a canonicalized representation for loops. Therefore, we can't really directly represent any loop without having some canonicalization taking place. So at the moment, for instance, the LLVM framework does not handle irreducible control flow at all. My plan is to actually canonicalize those by some code duplication to make the loops out those irreducible control flows, so that can be handled as well. So this code duplication comes with disadvantages like more code. But the advantage here is that this duplication only gets baked into the LLMVR, so at code generation, if we actually manage to apply some profitable optimization. Otherwise, the LLVM IR is just stays as it is, and the loop representation is just thrown away. So with transformations, I think you can represent all the different kinds of loops, including maybe not recursion, but irreducible control flow. Yeah.
Okay. If we don't use MLIR now, but Clang move to emitting MLIR, what will be the cost to move your implementation to MLIR then?
So I think the cost is negligible. Actually, in my prototype I'm working on, I'm actually partially already having an entry points for MLIR. So I have an abstraction about what an operation is. An operation can be an LLVM IR instruction or an LLVM instruction. But the only thing I need to know is the side effects, like memory accesses. For LLVM IR, I need to kind of, the operation class needs to know what the side effects of the LLVM IR has. For MLIR, there is fortunately a side effect interface that could be used for this one. But I think there's an abstraction layer. I have enough abstraction that such there would be no problem to apply these transformation on MLIR as well on LLVM IR, and if necessary, even on machine IR.
Thank you, Michael, for answering all these questions. We are a bit of out of time. And if you have more questions, feel free to keep asking. And I think Michael will try to answer you on the app, or you can come to the loop optimization booth tomorrow or the roundtable for the loop transformation working group. See you there.
Okay. Thank you, Ritna.